Hi everybody, my name is Antonio Allegro and I am a PhD at the Polytechnic University of Turin, under the supervision of Professor Tatiana Tommasi. In this video, I'll present you our work named End-to-End Learning to Grasp via Sampling from Object Point Clouds. This work has been done in collaboration with colleagues from the Burg project and the University of Birmingham. In this work, we tackle the task of grasping from 3D object point clouds. Given a partial observation of the real object to grasp, we aim to predict a set of successful grasp poses. To learn the desired mapping, we employ a deep neural network. We focus on predicting 6 dove grasp poses for a two-finger parallel jaw gripper. The grasp is formalized using a contact-based representation, which is defined as first contact point, the second contact point, and finally the grasp orientation. There are many challenges to face when solving this task. We identify the first one in the partiality of the 3D input point cloud. During both training and testing, our model has no access to the complete object geometry. Instead, can access only to a partial observation which is captured by a 3D sensor. This means that often a graspable portion of the object is hidden or simply not available. Another challenge is generalization. In this work, we focus on the generalization of the proposed algorithm to novel objects. This means that at test time, it is possible to have objects unseen during training. Finally, we have the complexity of the proposed algorithm. We measure this complexity in terms of the number of training samples required to train the algorithm and the inference time. We can divide the grasping pipeline into 3 stages. The first one is the grasp proposal, in which, given the partial point cloud is input, grasp anchors are retrieved. Then we have the grasp prediction stage, where a complete grasp is regressed, starting from the anchors of the previous stage. Finally, at the grasp ranking stage, predicted grasps are scored and ranked according to the likelihood of being successful. The score to each grasp is often assigned by employing a grasp classifier, and only the top scored grasp will be executed. In this work, we focus on the first stage, the grasp proposal. Previous works used geometric heuristics to identify the grasp anchors in the input point cloud. This is the case for the 3D space quantization logic of GPNet and the farthest point sample subselection adopted in Contact GraspNet. These heuristics often produce a large number of grasp anchors which are not optimized for the grasping downstream task, leading to many grasp predictions to be pruned or refined in the next stages. Moreover, since the proposal is not learned, the generalization of these heuristics to novel or different-sized objects is usually poor. Differently from previously employed geometric heuristics, in this work we aim to learn the distribution of visible contact points from the input point cloud. Inspired by SampleNet, we train a small neural network to solve a differentiable relaxation of the sampling task. Given the input point cloud, this network is trained to sample all visible contact points. For each of the sampled contact, we adopt 2 additional multilayer perceptrons to predict the second contact and the approach angle. In this way, we completely formalize contact-based grasps. Our approach is end-to-end. Grasp proposal and grasp prediction objectives are jointly optimized and naturally influence one another. We show through extensive experiments that our approach guarantees lower complexity and superior generalization abilities. For quantitative results, we show here some of our simulation experiments. We report on the left the ShipNet SEM to ShipNet SEM experiments. These are performed in a closed set hypothesis, meaning that at test time there are no unknown object categories. Differently, on the right, we report the simulation experiments for the ShipNet SEM to YCB scenario. These last experiments are more challenging. This because YCB contains object categories which are not present into the ShipNet SEM dataset. In both cases, our L2G model is able to outperform previous state-of-the-art by a large margin. Regarding complexity, our L2G model is very efficient in terms of the number of training samples required. By using only half of the overall training dataset, L2G is able to outperform its best competitor, GPNet. Moreover, our L2G model is blazing fast, with much lower inference times than GPNet. Finally, we present real-world robotic arm experiments. On the left, we test L2G with a set of custom objects which are close to the training set data distribution. On the right, we test with a set of YCB objects containing also unknown or novel object categories. Check our paper for details and more interesting analysis. Our code and robotic arm experiment video are available on the GitHub page. Thank you very much for your attention.